Today, we are mastering the financial applications of geometric sequences. In this lesson, you will learn how to model compound interest, annual depreciation, and the impact of inflation on investments. These concepts are fundamental because they bridge pure mathematics with real-world financial literacy. In the IB Diploma Mathematics Analysis and Approaches examinations, these topics frequently appear in Paper 1 and Paper 2, often as part of larger modeling questions where precision and clear variable identification are key to securing full marks. Let us begin with Concept 1, compound interest. Compound interest occurs when interest is calculated on the initial principal and also on the accumulated interest of previous periods. This is modeled by a geometric sequence. The general formula for the future value is PV times 1 plus R over 100k, all to the power of kn, where PV is the present value, R is the annual interest rate, k is the number of compounding periods per year, and n is the number of years. In the IB curriculum, financial models primarily use the properties of geometric sequences. Compound interest occurs when interest is calculated on the initial principal and also on the accumulated interest from previous periods. We use this general formula to find the future value, where PV is the present value or initial principal, R is the nominal annual interest rate as a percentage, K is the number of compounding periods per year, and n is the number of years. The term geometric comes from the fact that we are multiplying the principal by a common ratio every period. The frequency of compounding, denoted by k, is crucial. Yearly means k equals 1, half-yearly means k equals 2, quarterly means k equals 12. The more frequently interest is compounded, the faster the investment grows because you earn interest on interest more often. Let's look at an example of compound interest. An amount of $5,000 is invested in an account that pays a nominal annual interest rate of 4.5%, compounded monthly. Calculate the value of the investment after 6 years. First, we identify our variables. The present value is $5,000, the rate is 4.5, k is 12 because it is monthly, and n is 6. Plugging these into our formula, notice that the exponent is 72, which represents the total number of compounding periods over 6 years. We simplify the bracket to find our common ratio of 1.00375. After 72 months, the investment grows to approximately $6,546.52. Always ensure you round financial answers to 2 decimal places unless stated otherwise. While interest grows an investment, depreciation models the reduction in the value of an asset over time, such as a vehicle or machinery. In the IB syllabus, we use the reducing balance method. This is essentially a geometric sequence where the common ratio is between 0 and 1, meaning the value decreases by a fixed percentage each year. The formula is very similar to compound interest, but we subtract the rate from 1. Here, V is the value after n years, PV is the initial value, and R is the annual rate of depreciation. Mathematically, if an asset loses 15% of its value, it retains 85%. Therefore, our common ratio would be 0.85. This explains why we subtract the rate divided by 100 from 1. Let's look at an example of annual depreciation. A car is purchased for $25,000. It depreciates at an annual rate of 15%. Find the value of the car after 4 years. We start by identifying the knowns. The present value is $25,000, the depreciation rate is 15, and the time period is 4 years. Applying the reducing balance formula, we substitute our values. Multiplying the initial cost by the common ratio of 0.85 raised to the 4th power gives us the remaining value. Rounding to 2 decimal places, the car is worth $1,3050.16 after 4 years. Notice how the value drops significantly. This is the nature of exponential decay in finance. The nominal value of an investment tells us how much money we have, but it doesn't account for the loss of purchasing power over time. This is where inflation comes in. To find the real value, we deflate the future value using the annual inflation rate, represented as I in decimal form. Think of this as the inverse of compound interest. We are dividing to see what that future amount is worth in today's prices. Look at this comparison. Both curves increase, but the nominal value grows much faster. The green curve represents the actual buying power. Even though your bank balance is high, inflation eats a portion of those gains, leaving you with a lower real value. Understanding this difference is a high-level skill in IB Mathematics. An investment grows to $8,000 over 5 years. If the average annual inflation rate during this period was 2%, calculate the real value of the investment. In this case, we are given the future value of $8,000. The inflation rate of 2% must be converted to the decimal 0.02 for the formula. We divide the future amount by the inflation factor. This deflates the nominal sum back to its equivalent purchasing power from 5 years ago. Performing the calculation, we find the real value is $7,245.85. This means $8,000 in 5 years buys what $7,245 buys today. To visualize this, consider how nominal value and real value diverge over time. While the nominal value grows with interest, inflation erodes its purchasing power, resulting in a lower real value. In Paper 2, you are expected to use the finance solver on your graphic display calculator. Mastering these variables is essential for speed and accuracy. The standard variables on your calculator include N for the total number of periods, I% for the annual interest rate, PV for present value, PMT for periodic payments, and FV for future value. Finally, P/Y and C/Y represent payments and compounding periods per year. A common point of confusion is the sign of PV and FV. The GDC views finance as cash flow. If you give money to a bank to invest, PV is negative because it is leaving your pocket. When the bank pays you back later, FV is positive. If you enter both as positive, the calculator will often return an error or an incorrect result. Always think, is the money coming in or going out? Let's look at an authentic IB-style question. A collector buys a rare watch for $12,000. The value of the watch increases by 8% each year. Part A asks us to find the value of the watch after 5 years. Part B asks, if the average inflation rate over these 5 years is 3%, find the real value of the watch at the end of the 5-year period. For Part A, we treat the increase like compound interest. The watch is now worth $17,631.94. For Part B, we take our answer from Part A and deflate it. Note that while the nominal gain is over $5,000, the real gain in purchasing power is only about $3,200. Identifying that Part A's result becomes the future value for Part B is the key logic here. Even the strongest students can lose marks on financial questions due to simple errors. Let's ensure you avoid them. Students often forget to adjust K for the compounding frequency. If a question says compounded quarterly, K must be 4. If you use K equals 1, your entire calculation for future value will be incorrect. In multi-step problems like calculating real value, students often round the nominal future value to 2 decimal places before dividing by the inflation factor. This leads to premature rounding errors. Always use the exact value stored in your calculator for intermediate steps. As we discussed, failing to enter PV as a negative number in the finance solver is a frequent mistake. If the calculator gives you a no solution error, check your signs first. Do not simply subtract the inflation rate from the interest rate unless the question specifically asks for a real rate of return. For real value, you must calculate the nominal future value first, then divide by the inflation factor. To maximize your score in the IB exam, keep these strategies in mind. Even if you are using your graphic display calculator for Paper 2, write down the formula and the values you are substituting into it. If you make a typing error on your calculator, Examiners can still award method marks if they see you identified the correct variables. Start every finance question by listing your variables: present value, interest rate, number of years, and compounding periods. This organizes your thoughts and acts as a checklist for the formula. Unless a question specifies otherwise, always give financial answers to 2 decimal places. However, if the question asks for the answer to the nearest dollar, follow that instruction strictly, or you will lose the final accuracy mark. In IB command terms, calculate usually implies a numerical answer is required, often with working. Find is more general, but still requires a clear logical path. In both cases, the sequence of your logic is what secures the marks. It is time to test your understanding. Pause the video now and attempt these 3 questions. The easy question asks for the value of a $3,000 investment after 10 years at 5% interest. The medium question involves a $45,000 machine depreciating at 12%. You need to find when it falls below $20,000. The hard question requires calculating the real profit on a $10,000 investment at 6% interest, adjusted for 2.5% inflation. Take a moment to work through these. The medium question requires a bit of logarithms or GDC usage, and the hard question requires you to find the difference in real value. Let's review the solutions. For the easy question, we simply use the compound interest formula with k equals 1. The value is $4,886.68. For the medium question, we solve for n. Using logarithms or the GDC solver, we find n is approximately 6.35. Since the question asks for the number of full years to fall below 20,000, we round up to 7 years. For the hard question, we first find the nominal future value of $102,789. Then we deflate it to find the real value of $115,984. The real profit is the real value minus the original $10,000 investment, giving $1,509.84. To summarize our lesson on the financial applications of sequences. First, remember that all these financial models are just applications of geometric sequences. Interest has a ratio greater than 1, while depreciation has a ratio between 0 and 1. Second, the compounding frequency k is the most common place to lose marks. Always identify if you need to divide the rate and multiply the time by this factor. Third, distinguish between nominal and real values. Inflation reduces purchasing power, so the real value will always be lower than the nominal future value when inflation is positive. Finally, use your GDC finance solver to save time, but be meticulous with your signs: negative for money going out and positive for money coming in.